All right, welcome back to Talk Tensors. Today we're diving into a paper that caught our eye. It's called Revisiting Medical Image Retrieval via Knowledge Consolidation.
Okay.
And, when we talk about AI in healthcare, finding similar medical images quickly and accurately, well, it's pretty much the cornerstone, right?
Absolutely.
You've got doctors, they need to compare a new scan to tons of past cases. It's huge for, faster diagnosis, planning treatments.
Right. Yeah.
But here's the thing. We're just drowning in medical imaging data these days. Those old search methods, well, they're starting to show their age.
Yeah.
This paper, though, it's like a breath of fresh air. It's got this really smart approach to finding those similar images, even when they're a little bit off or they don't quite fit the usual pattern.
Yeah.
And get this, it even tries to rank them by how visually similar they are. Pretty cool, huh?
It sounds very interesting.
Let's break it down. Let's see what they did.
Let's do it.
So what's the core problem they're tackling here?
Okay. So they basically point out there are some big limitations in how we're doing medical image retrieval right now.
Okay.
The first one, and this is pretty fundamental, is that a lot of the existing techniques, they're not really squeezing all the juice out of the images.
That's interesting.
They might be stuck on those high-level features or just kind of mashing together different levels of detail without a clear strategy.
So they're not really, really looking deep. This just kind of scratching the surface.
Yeah, and that's where this paper gets interesting.
Yeah.
Because they're saying, hey, let's go beyond the big picture.
Okay.
Let's zoom in on those finer details and figure out how to use them.
Yeah.
Think about it. There could be tiny little visual clues that a doctor would pick up on.
Right.
But if the AI is just looking at the overall shape, it might miss them.
It misses the nuances.
Exactly.
Okay, so that's the first problem, insufficient representation learning. What else? What other problems are they pointing out?
The next one is what they call over-centralization.
Over-centralization. That's a mouthful.
It is. But the idea is actually pretty simple. Imagine you're trying to learn about all different kinds of dogs.
Okay, it's like dogs.
Right. But you only ever see those perfectly groomed show dogs. You'd miss out on all the scruffy, adorable mutts out there.
You'd miss out on my dog, for sure.
Exactly. And it's the same with medical images. Current methods, sometimes they get too focused on this idealized version of what a condition looks like.
I see.
And they miss all the normal variations you see in real patients.
Okay.
So this paper, it introduces this really clever concept of image fingerprints.
Image fingerprints, I like that.
Yeah. It's a way for the system to learn those subtle differences, even within the same diagnosis.
Okay.
So 2 images might both be of a tumor, but their textures, their shapes, those could be quite different. And these fingerprints help the AI grasp that.
Okay, so image fingerprints for over-centralization. Got it. What else did they point out as a problem?
Okay, now we get to the tricky stuff. Out of distribution data, or ODE. Think about images that have been messed with to try and fool the system.
Like adversarial example.
Exactly. Or even just images from different hospitals. Maybe they have slightly different scanners, different protocols.
So even if it's a legitimate medical image, it might still throw the AI off.
Right. And a lot of current methods, they really struggle with this. They can't always tell when an image is unusual.
That makes sense. They haven't seen that kind of data before.
Exactly. And that can be a big problem, especially in healthcare, where accuracy is so crucial.
You don't want the AI making a wrong call just because it's never seen a scan from a particular type of machine.
Exactly. And then, last but not least, they point out that a lot of systems, they don't actually rank the images they retrieve by how similar they look.
Oh, interesting.
So you might get a bunch of images of the same organ, but not necessarily the ones that are most visually similar to your query.
So it's not really a helpful search result if it's not showing me the most relevant images first.
Exactly. They might be in the same ballpark, but not the closest match.
Okay, so we've got 4 key challenges. Not learning enough from the images, over-centralization, struggling with out-of-distribution data, and not ranking by visual similarity. What do they propose to do about all of this?
Okay, so their answer to all of this is ACIR, Anomaly-Aware Content-Based Image Recommendation.
ACIR. Okay, so the name kind of gives it away, right?
It does. It tells you exactly what they're going for. Anomaly detection, content-based, focused on recommendation.
So it's not just about finding any similar image, but the right one, and making sure it's not something totally out of left field.
Right.
So how does ACIR work? What's their magic sauce?
Okay, so They tackle these problems with this really cool concept called knowledge consolidation. It's a multi-pronged approach.
Multi-pronged, I like it. So what's the first prong?
The first prong is depth-aware representation fusion, which they shorten to DARF. And what they're doing here is really smart. They're taking the shallow, basic visual info in the image, like edges, textures, that kind of thing. And they're combining it with those deeper, more abstract features that the AI learns.
So it's not just about having both types of features, but actually knowing how to blend them together.
Precisely.
Got it. So DARF, that's prong one. What's next?
All right, so to make DARF even better, they use a special kind of neural network called a pixel vision transformer, or PyT. And PyT, it's really good at seeing the big picture.
Okay.
It understands how all the different parts of the image relate to each other at a high level. So it's like having an expert chef who not only knows the individual ingredients, but also understands how they all work together to create a delicious dish.
Okay, so DARF brings in all those different levels of detail, and then PyT helps make sense of it all. Got it.
Yeah.
What's the second prong in their attack on this problem?
Prong number 2 is structure-aware contrastive hashing, or SCH.
There's that fingerprint idea again.
Yes. This is where those fingerprints really shine. So to deal with that over-centralization issue, they create these low-resolution versions of the medical images.
Mini-me versions of the images, no?
Exactly. And by comparing these fingerprints, they can really understand the structural similarities and differences even between images that are in the same diagnostic category.
So it's not just saying, these two are both tumors, so they're the same. It's saying, okay, these two tumors actually have similar structures, so they're probably more closely related.
You got it. And here's another important thing. They moved away from using something called relaxed Hamming distance, which is a kind of fuzzy way of comparing those image fingerprints.
Fuzzy measurements. Sounds like trouble.
Yeah, it can be. That fuzziness can make the AI learn less effectively. So instead, they switch to the Pearson coefficient.
Okay.
Think of it like using a really precise ruler instead of a wobbly measuring tape.
So sharper, more accurate comparisons. Got it.
Exactly. That leads to a much more stable and accurate learning process.
Okay, 2 prongs down, 2 to go. What about those tricky out-of-distribution images? How does ACIR handle those?
For ode detection, they built a special self-supervised module. And the basic idea is this. They train part of the system, called a decoder, to try and rebuild the original image from the features it has learned.
Okay.
So if the image is something truly weird, something the model has never seen before, it's going to have a hard time putting it back together.
It'll be like trying to solve a jigsaw puzzle with half the pieces missing and in the wrong box.
Exactly. And that's the signal. The bigger the error in the reconstruction, the more likely it is that the image is an outlier.
Ah, so it's like a built-in anomaly detector. Very clever. Okay, last prong time. What about making sure the results are actually ranked by visual similarity?
Okay, so once ACIR has found a bunch of potentially relevant images, it reorders them.
Okay.
And it does this based on the average similarity of their embeddings, those rich feature representations that we built using DARF and SCH.
So it's like double checking to make sure the most visually similar images are at the top of the list.
Exactly. It's not just about being in the same category, it's about looking alike too.
Awesome. Okay, so we have a decent overview of what the problems are and how ACIR proposes to solve them. Now, I really want to dig deeper into how they built and tested this thing. Can you walk me through those details?
Sure, let's do it.
Let's start with the solutions again, just to recap.
Okay, so to recap, the 4 key solutions they highlight are DARF, that's depth-aware representation fusion, for combining different levels of detail from the images.
Yep.
We've got structure-aware contrastive hashing, SCH, which uses those low-resolution image fingerprints to get a better handle on the variations within medical images.
Fingerprints check.
Then we have the self-supervised learning module for ode detection to catch those unusual images.
Outlier alert. Got it.
And finally, content-based similarity ranking to make sure the most similar images are at the top of the list.
All right, so those are the solutions, high level. But how do these actually address the specific challenges they laid out in the beginning?
Right, so remember how they talked about not getting enough information from the images?
Insufficient representation learning.
Yeah, right. Well, DARF in the Pixel Vision Transformer, those directly address that.
Makes sense. They're all about learning richer, more detailed features.
Exactly. And then there's the over-centralization problem, where the AI gets fixated on just one type of image for each diagnosis. SCH tackles that head-on with those fingerprints.
The fingerprints help the AI appreciate the diversity within each category.
Precisely. And those OD images, the ones that could really trip up the system.
Yeah, the weird ones.
The self-supervised decoder takes care of those. By looking at the reconstruction error, it can flag those images as being different from what the AI has been trained on.
So it's like a safety net, making sure the AI doesn't get fooled by something unexpected.
Exactly. And finally, to make sure the search results are actually useful, they use content-based similarity ranking. So the most visually similar images are right there at the top.
Okay, so each piece of their solution targets a specific weakness. Nice. Now let's get down to the nuts and bolts. Tell me about the model architecture.
Okay, so ACIR uses what's called a hybrid encoder. And this is where things get really interesting. They start with a classic convolutional neural network, or ConvNet.
ConvNet's the bread and butter of image processing.
Exactly. They're really good at picking up local patterns and textures in images. But then they add in that pixel vision transformer, the PyT, which is better at seeing the big picture.
So it's like combining a microscope with a telescope.
I like that analogy. They're also using these things called conv-MSAs, which are convolutional multi-head self-attentions.
Conv-MSAs. All right, that's a mouthful.
It is. But think of them like this. They let the AI focus on different parts of the medical image, just like a radiologist would.
Okay.
The convolutional part helps it see local details, and the self-attention part helps it understand how all those details relate to each other across the entire image.
So it's getting both the fine-grained details and the overall context.
Yes. And then they have the DARF module, where they combine all the features extracted by these different parts of the encoder.
So it's like blending all those different perspectives into one super feature representation.
Exactly. And to turn those features into those compact hash codes, they use Kolmogorov-Arnold networks, or CANs. These CANs are very adaptable. They can learn to represent the visual information in a really nuanced way.
Okay. And of course, we have the decoder, the part that's responsible for spotting those OD images.
Right. And you can actually see a diagram of this whole architecture in figure 2 of the paper. It's pretty cool.
So it's this intricate dance between different types of neural networks, each with its own strengths. But how do they actually train this whole system? It seems pretty complex.
It is complex, but they've put a lot of thought into the training process. They use a combination of loss functions to guide the learning.
Loss functions.
Yeah, these are like mathematical guides that tell the AI how well it's doing and what it needs to adjust. So first, they have the structure-aware contrastive loss, or LSC.
Structure-aware, so it's taking those fingerprints into account again, right?
Yes. It helps make sure that images with similar structures are considered more similar, even if they have some visual differences. And then they have the quantization loss, or LQ, which helps make the learned features more suitable for hashing.
Quantization, meaning turning those continuous values into discrete ones for those hash codes.
Exactly. And they combine those two into a weighted structure-aware contrastive loss, LWSC. That helps address any imbalances in the data set. Some diagnoses have way more images than others.
So it's making sure the training is balanced and fair.
Right. And remember that Pearson coefficient we talked about. They use that directly in their loss function to measure the similarity between image features.
So it's all about making those comparisons as precise as possible.
Yes. And for the OD detection part, they look at the reconstruction error. So they use a metric called MSIM for grayscale images and the L1 norm for RGB images.
Those are standard ways of measuring how different two images are.
Exactly. And for the content-based ranking, they use the Pearson correlation coefficient again. But this time, they calculate it between the features of the query image and the retrieved images.
So it's really baking that visual similarity into the ranking process.
Absolutely.
Okay, so they've got this multifaceted training approach, but did it actually work? Did they get good results?
They did. They tested ACIR on 2 big medical image datasets. One's called Radio ImageNet CT. It's a huge collection of CT scans from all different parts of the body.
A good test for a system that needs to handle a wide range of medical images.
Right. And the other data set is the breast cancer semantic segmentation data set, or BCSS.
So a more specialized data set focused on breast cancer?
Exactly. And they compared ACIR against a bunch of other state-of-the-art hashing methods. And the results are in Table 1 and Figure 3 of the paper.
Drum roll, please.
ACIR beat them all, in some cases by a lot. Like on the radiology data set, they saw improvements ranging from 5.6% to almost 39%.
Wow, that's a huge jump in performance. So it's not just a theoretical improvement, it actually works in practice.
Exactly. And they didn't just stop there. They also did ablation studies.
Ablation studies, what are those?
It's basically where you remove different parts of the system one at a time to see how much each part contributes to the overall performance.
So like a controlled experiment to see what's really driving those improvements.
Right. And they found that each component of ACIR, the LWSC loss, the DARF module, the KN layers, and the content-guided ranking, they all played a role in boosting the performance.
So it's not just one magic trick, it's the whole package working together.
Exactly.
Okay, what about the ode detection? How well did it do at spotting those unusual images?
The ode detection results are in Table 3, and they're really impressive. They threw a bunch of images at ACR that it had never seen before, and it was able to correctly identify them as out of distribution with high accuracy.
That's really important for real-world applications, especially in medicine. You don't want the system making decisions based on data it doesn't understand.
Absolutely. And they even visualize the results in figures 4 and 5. You can see how ACR creates these really nice, distinct clusters for different image types, and the ode images are clearly separated from them.
So it's not just numbers. The visualizations also confirm that ACR is doing what it's supposed to do.
Right. They also did some other tests, varying the number of hash bits and looking at performance under different conditions, and ACR was consistently robust.
Robust, meaning it didn't fall apart when they changed things up.
Exactly. And they also looked at the computational cost and inference efficiency.
So how fast it is, basically.
Yeah, and they found that ACR strikes a good balance between performance and speed.
Okay, so we've talked a lot about the technical details, but before we move on, I want to step back and think about the bigger picture. What's the historical context for this research?
Sure. So medical image retrieval, it's been around for a while. And in the early days, people were doing it all manually.
So like actually looking at images and picking out features by hand?
Pretty much. But then deep learning came along and changed the game. Suddenly, we could learn these features automatically from massive data sets.
And that's where those hashing techniques come in, right?
Yeah.
Because you need a way to efficiently search through all that data.
Exactly. And ACIR, it builds on all of this. It takes advantage of the latest advances in deep learning, contrastive learning, and hashing to create a really powerful and robust system.
So it's standing on the shoulders of giants.
Definitely.
Okay, so what are the key takeaways here? What makes this research so special?
I think the real novelty is in how they combine all these different ideas into one system. The depth-aware fusion, the structure-aware contrastive learning with the fingerprints, the ode detection module, and the content-based ranking.
Yeah.
And of course, the clever use of the Pearson coefficient.
It's not just one breakthrough, it's a symphony of breakthroughs.
Exactly.
All right, so let's zoom out even further. What are the real-world implications of this research? How could ACIR actually change things in healthcare?
I think the potential is huge. Imagine doctors being able to instantly access a database of visually similar cases right at their fingertips.
That would be a game changer.
It could make diagnosis faster and more accurate. Treatment plans could be tailored more precisely.
That could even help with medical education.
Exactly. And because ACR can handle data from different hospitals, it could facilitate collaboration and research on a much larger scale.
And that O detection, that could be a real lifesaver. It's like having a second pair of eyes, making sure the AI doesn't make a mistake when it encounters something it's never seen before.
It's all about increasing trust and reliability in these AI systems.
Okay, so before we wrap up, it's time for our favorite segment, Novel Notions.
All right, let's get speculative.
What are some crazy, out there ideas that this research inspired?
Okay, here's one. Integrating uncertainty estimation. What if, on top of everything else, ACIR could also tell us how confident it is in its predictions?
So like a confidence score for each image retrieval? That would be interesting.
Exactly. And you could combine that with the reconstruction error for O detection.
Wow.
So if the model says, hey, I found a similar image, but I'm not really sure about this one, that would be a huge red flag.
It's like the AI raising its hand and saying, I might need some help here.
Exactly. And there's a lot of research in Bayesian deep learning that suggests that this kind of uncertainty estimation can make AI systems much more reliable, especially in high-stakes fields like medicine.
It's all about making sure the AI knows its limits.
Right. And another interesting thought, what if we could use ACIR for cross-modal retrieval?
Cross-modal, what do you mean?
So imagine being able to search for CT scans using an MRI image as the query, or vice versa.
That would be super useful.
It would. And what if we could do this without explicitly using text data from the reports?
How would that work?
Well, maybe we could train ACIR to learn a shared embedding space where images from different modalities are close together if they have similar visual structures and semantic content.
So it's like the AI is learning to translate between different imaging languages.
Precisely. And the fingerprints could play a role here too, maybe helping the AI identify those modality invariant structural features.
That's pretty mind-blowing. But as always, we should remind our listeners that these are just speculative ideas. More research is needed to see if they would actually work.
Absolutely.
Well, this has been a deep dive and a half. We covered a lot of ground today, from the challenges of medical image retrieval to the intricate details of the ACIR system.
It's a really exciting piece of research.
It is, and the potential impact on healthcare is huge. To all our listeners, we highly recommend checking out the full paper. We'll have a link in the show notes. And who knows, maybe you'll be the one to take those novel notions and turn them into reality. Thanks for joining us on Talk Tensors.
Thanks for having me.